hi everyone, I'm Mehul Batra, and so today I'm going to present about Lake, Stream, and everything in between. It's about Apache Fluss and how you can use Fluss to make a streaming Lakehouse, or I would say a Streamhouse. So let's get started. A bit about me. Who am I? I'm Mehul Batra. I'm PPMC of Apache Fluss Incubating. I'm maintaining Fluss Iceberg and Fluss Link module. Currently, I'm a founding engineer at the AI Data Cloud team at DigitalOcean. I have a total 8 years of experience in big data and distributed system. So yeah, let's talk about what is Fluss and why it was created. So let's start from the top left. If you see, for row-oriented streaming use cases, we have Kafka, Pulsar. For row-orient batch use cases or transactional use cases, we have MySQL, Postgres, and then it came the era for analytical systems. For batch, for column orient, we have Iceberg, Snowflake, Hoodie, Pymon, long list keep going on. But we were missing something. In the column orient streaming, we didn't have anything. So that is where the Fluss was created. The main reason of Fluss was we wanted something with a columnar orientation, which can be used for your streaming storage and can do analytics as well. So let me give you a brief overview about Fluss and how the architecture looked like. So basically, in the left, you could see we have n number of data sets from where the data gets generated. It could be from your databases, it could be from your logs, it could be from your app click streams, or it could be from the IoTs. So there are engines in between which can streamingly write or put your updates onto the Fluss, and Fluss would be your storage layer, which will be on the center. And on the extreme right, you could see you have multiple set of engines. It could be your Flink, Spark, which could do your streaming reads, batch reads, lookup joins, or union reads. And then on the bottom, if you see, Fluss can connect with your Lakehouse storage as well for your lake tables, which is sitting on your TS storage, which could be your S3, GCP, Blob, Spaces, HDFS, whatsoever. So let's talk about the Fluss cluster internals. So basically, Fluss was created to bridge the gap between your streaming data and your data lakehouse by enabling the low latency and high throughput data ingestion and processing while seamlessly integrating with the popular compute engines like Flink and Spark. So if you see, in the beginning, we have a coordinator server. So basically, the coordinator server serves as a central control and management component of the cluster. It is responsible for maintaining your metadata, managing your table or tablet allocation, then listing your nodes, handling permissions. Then right next to it, if you see, you have your tablet server. So tablet server is nothing but like your data nodes. So tablet server is responsible for your data storage, persistence, providing IO services directly to user. And the tablet server comprises of two components, which will come later, which is one is your log store and another is your KV store. And then last but not the least, it's the Zookeeper. So Zookeeper currently used for cluster coordination, metadata storage, and cluster configuration management. So this is how the Fluss overall big bird eye view of the architecture looks like. Now let's jump into the logical models in the Fluss. So on the left, if you see, we have a log table, which is append only. And on the right, if you see, we have a primary key table, which is mutable. So before we jump into the diagram, I would just wanted to touch base on like what is log table is. So log table is basically a type of table in Fluss that is used to store the data in the order which it was written. So log table currently supports append records and doesn't support any update or delete operations. And usually log tables is used to store logs in a very high throughput. Typical use cases like Apache Kafka. Log table is created by not specifying any of the primary key clause when you try to run any DDL. And then comes your primary key table. So primary key table was created to ensure the uniqueness of the data that you are putting by specifying a primary key. So your primary key table supports insert, update, delete operations, and a primary key table can be easily created via DDL. Both of log and primary key table shares the same DDL. Just the only difference is you have to just specify a primary key clause and it will automatically convert it into a primary key table. So if you see closely the diagram, you could just directly create a table where we have created a table called visits, which has a user ID, which is your begin and your item and your timestamp. So we could start appending the data. So like a user of 100 user ID purchased an iPhone at a certain date, and then he purchased a MacBook. It got appended to log table, and then a reader, or I would say a consumer, is consuming from that log table. So if you see the order is intact, so he'll see the first event is again the iPhone event and then the MacBook. Then if we go to the primary key table example, we firstly put the information, like firstly we started creating with the table. So if you see, we created a table called user profile, which has like a user ID, name and location, and then we just have mentioned the primary key clause. So the moment you mention the primary key clause, it will become your PK table. So if you see, we inserted a key value pair which has the user ID, the name, and the location where the person is based off. So the person was first located in EU, and then we again put a new key value pair which has the same user ID for the person. Now the location has been changed to US. So if you see how the emit is working, so there is a changelog stream which is append only, which a user can consume, which will have all your uh, change types. So if you see, the first change type was of insert, which is like John EU, and then update before, where we could see the new key has come. So EU location is being replaced by an update after, which is now being replaced to US. And you can easily consume all these changelog streams by using Fluss virtual tables. So if you see in the bottom, we have written a simple SQL examples where you just have to write your table name, and then you have to put a suffix by name, change log, or it could be bin log, and then we also give you a row kind. So by selecting the type of row kind, you could just consume the change log that you want. So basically Fluss capture all the changes when inserting, updating, or deleting records in your primary key table, and it also captures the inserts for log table. And all these things get stored into your changelog and binlog table, and downstream consumers can directly consume the changelog to obtain the changes of these log table or primary key table via the virtual tables, or you could say system tables, without the stress of maintaining a separate storage or a state maintenance, or without using any external tools like Debezium. So now come the star of the presentation. You could say Streamhouse or streaming Lakehouse. So why, or what is Streamhouse and why it is needed? So basically, a Streamhouse is a streaming lakehouse which represents a unified architecture that merges your streaming and batch systems under a single model, rather than stitching them together as a separate components. So the core principle of the Streamhouse is you have a single write path. Application will write once to Fluss, and the data automatically flows from your hot to cold storage based on the configurable retention. So this basically eliminates the need of dual write coordinations. And by eliminating your dual write coordination, you can get rid of data duplication, consistency issue, the operational complexity that you inherit with the Lambda architecture. So by achieving this, you could maintain a Kappa architecture for your analytics. So it's more or less said single read, single write. So if you see in the table, we have a hot and cold tier approach. So on the left side of my diagram, the hot data sits in Fluss. which can retain data up to 1 hour to 1 day. It's backed by your NVMe or SSDs, and it has a latency of sub-second or milliseconds. Then on the bottom of the diagram, you could see the Lakehouse storage, which automatically the data get tiered via the tiering service, which will eventually come down the line. We'll talk about it. But the cold data is in being stored in your S3 or object storage, which can store data up to hours to years of history, which has a latency of minute level. So in the diagram, you could see you could read that data via union reads. So you have a single table abstraction. You can just query that table, and it automatically behind the scenes will get your latest as well as your historical data based on your timeline. The data get automatically tiered via automatic life cycle management, and all the data that you have sitting has a sub-second of freshness. So real-time updates are immediately visible, not waiting for your batch commits. And your query engine sees one logical table by spanning both the tiers. You might ask, like, why is it needed? So as we see the way we are moving towards the AI era, so everything needs to be real time. Your business decisions need to be real time. Your AI ML models require the fresh data to give you a new, on the spot recommendations and personalizations. Your AI agents need real time context. So your chatbots and assistant must be able to answer on your current state with respect to your orders, your inventory, your accounts, not yesterday's snapshot. And then we were talking about the tiering service. So basically, tiering service is what we call, and we also like to call it zero ETL, which is basically vendor lock free and open source, that continuously reads the data from Fluss, converts it into from arrow format to Parquet, and commits to Iceberg with exactly one semantics by just setting a single config. So if you see on the top left side, you just need to create a DDL, and under that DDL, when you are creating your log table or primary key table, if you see the with clause, you just have to mention that table data lake enabled. It will automatically start tiering your data. And if you ask me, okay, Mehul, we didn't mention the table format. So that table format is being set at the cluster level properties. So by setting this single property, Fluss will start tiering your data based on the data lake freshness time that you have set here. So it automatically uses the embedded compaction strategy, where writer handles both new data ingestion as well as your small file cleanup async with a single atomic workflow. By that I mean you can just enable your table.data.auto compaction, and it will automatically compact your small files. So if you see in today's era, if you want to write our ETLs to move data from any real-time layer to any lake storage, you have to go with the n steps of the UI, or dealing with complex YAML or Kafka Connect JSON, which is very odd to break. So with this DDL, it's very simple. You just have to get with the one config, and voila, the data will start tiering. And currently, zero ETL supports both of your table types. It can tier data from log table as well as from your primary key table by keeping your mapping schema, whatever schema that you had in your Fluss tables. It will directly intact with your lake table. It also uses the unified data locality via partitioning. So whatever data partitioning that you had in your Fluss table, it will automatically get replicated in your Lakehouse to power your clickstream and dimensions.
Mehul, I think if you want to wrap up in a few seconds,
yep.
Before, because we don't have much time for Q&A, so I want to ask you very rapid fire Q&A.
Yeah, that's fine. I'll just wrap it up. I'll just wrap it up in like 2-3 minutes. Okay, that's fine.
Oh, no. 25 seconds.
Oh, 25 seconds is too much.
Yeah.
Or like it's too less. Just give me at least 2 minutes.
Go for it. We got 1 minute, and I'll try to hold the dam,
Sure.
the walls of the dam until then.
Sure. So basically, with a single flag, you can turn on your compaction strategy. And so again, everything is in Fluss, it's tables. There's no concept of topic. And you get a first class schema support for with the schema enforcement, and you have a primary key constraint which can help you to do your update supports. And one of the killer feature of the Fluss is the union reads. So whatever data is being sitting in your Fluss as well and in your lake act as a single abstracted table. So via union reads, you can ask your engine like Flink to directly read, and it will automatically out of the box will read your data from Fluss as well as your iceberg. So if you see in the bottom, we have a query. So if you want to directly apply the union read, you just have to write the table name, select name, order ID from the orders, and you need to give the event time. It will automatically stitch the data from both Fluss as well as your lake store. And if you only want to read from lake, you have to give a suffix called lake, and it will directly read only the data from your lake. So basically, how does it work? So Fluss underneath have a offset coordination. So Fluss coordinator server provides a snapshot as a iceberg boundary. So at this snapshot, Fluss takes care, okay, this much data is been this much data has been snapshot and tiered to lake, and up till again forward to that is sitting in Fluss. So when you try to read, the data distribution will look like the iceberg contains the old data, which is your order 1 and 2, and the Fluss contains the latest data, which is your order 3, 4, and 5, which are your new events which appeared after snapshots. So when you run the union read, the query engine will perform a union read. It will get your old orders up till the offset boundary for order 1 and 2 from the iceberg, and the new from your Fluss. And it's just a simple concatenation. The result will be concatenated in an offset order, so no duplication is required. Voila, and you'll see the union data. And lastly, I'll be talking about the traditional architecture versus the Streamhouse architecture. So earlier, if you see how it used to look like, was you had your logs, OLTP sitting, then all that data intermediately will be flown to Kafka. From the Kafka, you have your streaming or batch pipelines, which will read, and then that pipelines will write to the multiple copies. For intermediate stage, for rest of the consumers, or for some stages, you will write to Kafka topics. For your real-time analytics, you'll be writing into the real-time OLAP stores like ClickHouse, Druid. And for analytics, you'll be writing to Lakehouse to get your T+1 R. So you will see there's a lot of duplicate copy, and you don't have a single write path, which could cause data redundancy, data duplication, and inconsistencies. So your most of in your cases, you use Kafka and real-time OLAPs for your alerting or real-time dashboarding, and the Lakehouses are being used for the BI analytics or EDA for notebooks. But if you replace it with Fluss today, the complexity goes away. So you have the same above architecture where you have logs and OLTP sitting. Via Flink, you can directly read your logs. Via Flink CDC, you can directly read from your OLTP, and Flink has connectors to write directly to Fluss. Once the data enters to Fluss, you can enable the auto tiering. With a single copy, it takes care of the hot data is sitting in the Fluss storage powered by Apache Arrow columnar format, and the cold data goes to Iceberg with the Parquet file format, again columnar format. And with the union read, you can do both your alerting and dashboarding with a T+1 second of latency, and for batch, you can do your B1 or BI or notebook analytics with T+1 R.
Mehul, we gotta wrap up. But
Yep.
this was absolutely fascinating, and you've caused a lot of momentum and questions. So we're not gonna be able to take them on the stage, but please stick around in the chat, and I want you to answer these questions, because the more you speak, the more questions people have, which is a very good sign. So,
Sure.
Mehul, thank you very much.
Thank you. Thank you.
We really appreciate it.
Thank you.
Okay.